So the title of this video is Olé Mole. You don't actually pronounce mole to rhyme with Olé, though I'm a really big fan of mole sauce myself, but the exclamation certainly conveys my excitement about the universal unit of chemistry, and also encourage you that even though the explanation of how we came up with the mole can sometimes be a bit confusing, you can do it. Although we're technically supposed to know how to use the mole in calculations, there's a reason I'm taking the time to show about how we came up with it. So here goes nothing. Back in the day, again, the 1800s day because we were in atomic theory land, scientists wanted to come up with a universal unit for measuring atomic mass. Ideally, this unit would be approximately the weight of either a hydrogen atom or a single nucleon, since the mass of an atom comes from its protons and neutrons, not its electrons. However, scientists couldn't just arbitrarily say an atomic mass unit, or an AMU, is arbitrarily equal to a hydrogen atom. It had to stem from a particular measurement, and they had to put the measurement in terms of an element that they could easily measure. It turns out that it's really hard to quantify hydrogen, but it's easier to look at carbon and oxygen because they're contained in so many naturally occurring compounds. Initially, the element standard was oxygen, but once they figured out oxygen had isotopes, that system of reference became problematic. So in the 1950s and 60s, we recalibrated our expectations and defined the atomic mass unit as 1/12 the mass of a carbon-12 atom, or a carbon atom that has 6 protons and 6 neutrons. As a student, this always seemed random and arbitrary to me, so the way that I like to think of it as an educator talking to students is that we wanted to set the mass unit as approximately the weight of a hydrogen atom, or our smallest unit of element measure, but we achieved this by back calculating from something we could experimentally and accurately experimentally measure, specifically the mass of a carbon-12 atom. From the previous lecture, we know the masses of protons, neutrons, and electrons in kilograms. So if we do the math for what the mass of a carbon-12 atom is, and we divide this mass by 12 for each of the nucleons in the nucleus, we come up with a value for 1 AMU being 1.6605 times 10 to the negative 27 kilograms. You'll note here that although I've included the mass of the electrons, the difference between the mass of an electron, which has an exponent of 10 to the negative 31, versus a proton or a neutron, which is 10 to the negative 27, is 4 orders of magnitude. So the mass of an electron is negligible compared to that of a proton or a neutron, and therefore can be assumed to have a very small, if negligible, contribution. So essentially, when we think about the mass of the atom, we're thinking about the contributions of the particles that are in the nucleus. Now, if we take a look at the average atomic mass of hydrogen in the periodic table, once we've accounted for isotopes, the average atomic mass of hydrogen is 1.0078 AMU, or right around 1 AMU. Now let's take a minute to address the elephant in the room here. Holy exponents, Batman! That's a small number. My mind can barely handle a number with any decimal places at all, let alone 26 decimal places. As humans who deal with the world at a macroscopic level, this unit, this 1.6605 times 10 to the negative 27 kilograms, is not useful. So we came up with the concept of a mole to allow us to talk about amounts of an element on a level that makes sense to us, or to come up with a way to get rid of those pesky exponents. So the way we came to define a mole, also conveniently using the carbon-12 atom, was to say that if the atomic mass of carbon-12 is 12 AMU, a mole is the amount of carbon-12 atoms that exist in 12 grams of carbon-12. Practically, this allows the number of grams in a mole of a compound to be equal to the average atomic mass of that element. So the number of grams would be equal to the number of moles that are in, or number of mass units, or AMUs, that are contained in the atomic mass. How do we get there? The key is Avogadro's number. Avogadro's number is the conversion factor that allows us to travel between moles and numbers of objects, including the numbers of atoms. Let's do the math. The mass of one AMU is 1.6605 times 10 to the negative 27 kilograms. And we multiply this number by 12 because we know that one AMU is 1/12 of a carbon-12 atom, so we have to multiply by 12 to get back to the C12 atom. Now we're at the molecular weight, or the atomic weight, in kilograms of a single carbon-12 atom. We then have to convert from a single atom to the number of atoms in a mole, which we can achieve by multiplying by Avogadro's number. If we do the math, we get 0.01199, and the 9's trail off, or 0.012 kilograms, which converts to 12 grams. So here we look at mass in terms of the carbon-12 atom, but we can now assume that a mole of any element is equal to the Avogadro's number of atoms, which is equal to the gram amount of the atomic weight in AMU. So for instance, if we look back at the periodic table, and we see that the average atomic weight of oxygen is 15.999 AMU, that means for a mole of oxygen, we would need 15.999 grams of oxygen to achieve 1 mole. Because of this, we oftentimes will call the average atomic weight the molar mass. Other units that are interchangeable with AMU, therefore, are grams per mole, which makes sense as the AMU is equal to the grams of the element required to make a mole, as well as the Dalton, abbreviated DA, in honor of John Dalton. There are 2 final notes I'd like to make here. First is that you can and will have fractional amounts of moles. Amounts such as 0.5 or a half of mole or 2 moles can and will happen, as well as much smaller amounts of moles of a compound or a protein or another molecule, especially if you're a biochemist. The other is that we can apply what we know about moles to compounds or molecules that will contain multiple atoms of different identities and elements that are linked together. For example, a compound that we're all familiar with is water, or H2O. Water contains 2 hydrogens and 1 oxygen. Therefore, the molar mass, or the grams of a compound to make 1 mole, is equal to 2 times the atomic mass of hydrogen, so 1.0078, plus 1 times the atomic mass of oxygen. And if we do the math, that comes out to be around 18 AMU, or 18 grams per mole of oxygen. Or excuse me, water, not oxygen.